Today, we want to continue looking at parameterized curves, and we're going to start by looking at this line. Let's first find the equation of a line containing the points 2, -1, and -4, 7. So let's start with the traditional way of doing this and write y as a function of x. We know when we're dealing with a line, we can write y as a function of x. Could write x as a function of y, but let's start with the traditional y is a function of x. To find the equation of a line, we need a point and a slope. So in this case, we've got 2 points, but we need to calculate our slope. Slope is going to be rise over run. So if I look at the vertical change, our change in y is going to go from 7 down to -1 for a decrease of 8. So our change in y is a decrease of 8. Our change in x, in the x direction, we're going from -4 up to 2. So our change in x is 2 minus a -4, or a +6. We can combine these numbers into the slope. So the slope is change in y divided by change in x. And in this case, that'll be -8/6. We can simplify to -4/3. So we just take the change in y, -8, and divide by the change in x, +6. And then we'll simplify that to -4/3. Now we can use the point slope equation of a line. We can take either one of these points to be x0, y0. So we're just going to write y equals y0 plus m times x minus x0. And either one of these points will stand in for x0, y0. So I could write the equation y equals, start off at -1 and decrease by 4/3 whenever x is different than 2. So here's one choice for the equation of a line. We could also use the other point. Could write y, we could say start off y at 7 and decrease by 4/3 whenever x is different than -4. So here, this x plus 4 means if we plug in -4, then we subtract 4/3 0 times, and we have 7. But in the first one, if x is equal to 2, then 2 minus 2 is 0, and we start with -1 and subtract 4/3 0 times. So that'll give us the point that we want. If we plug some other point into, say, x plus 4, like x equals 2, 2 plus 4 is 6, so we'll subtract 4/3 6 times. Subtracting 4/3 6 times is like subtracting 6 divided by 3, or 2 times. 7 minus 4 is 3, minus 4 again is down to -1. So we can see that this fits. Now, what we really want to do is we want to parameterize this line. I know we said parameterized curves. Lines are just very uncurvy curves. Really, when I talk about a curve, I just mean a one-dimensional thing, a one-dimensional collection of points. There's only a forward and a backward. That's what we mean by curves. So there's no real reason to say straight lines, because lines include that straight part, that constant rate of change. So if we want to parameterize the equation of a line, I need to just write how x is changing with respect to some parameter and how y is changing with respect to some parameter. So Let's parameterize the line containing the points to -1 and -4, 7. What we need to do is take each of these points and assign a value of the parameter to them. So I'm going to take one of the points to be at t equals 0, and another point to be the point when t is equal to 1. Now, these choices could be whatever we want. We weren't restricted to which direction the line was supposed to go. But the easiest thing to do is to pick a starting point when t is equal to 0 and pick the next point when t is equal to 1. So we're going to assign parameters. I'm going to say t equals 0 happens when at the point 2, -1. And I'm going to say t equals 1 means that we'll be at the point -4, 7. We are choosing the parameters. We decide what these parameters are. Zero and 1 are easy choices. So when I make this choice where t is equal to 0 at 2, -1, so this is when t is equal to 0, and then t equals 1 at -4, 7, I'm saying that I want this line to go in this direction. So we'll start off here at 0 and then go towards 1. Then we just have to describe how x is changing with respect to t and how y is changing with respect to t. So we're going to think linearly. We're going to say x of t. We're going to write down where x starts. So when t is equal to 0, x is equal to 2. That's where x starts. When t is equal to 0, x is equal to 2. And then x decreases by 6 when t increases by 1. So x equals 2 when t equals 0, and x decreases by 6 when t increases by 1. So that means the rate of change of x with respect to t, x decreased by 6 when t increased by 1. So we start off at 2, and our slope change in x with respect to t is -6t. Note that if I plug in t equals 0, I get 2. And if I plug in t equals 1, I get -4. That's what we wanted to happen when we assigned these parameters. This was our choice. So this fits. If we calculate x of 0, 2 minus 6 times 0 is equal to 2. And if we calculate x equals 1, then 2 minus 6 times 1 is -4. The x's check out. Now we'll just come up with a linear function for y with respect to t. So y of t, when t is equal to 0, y is equal to -1. And so when, let's phrase it in the same way. let's say that y equals -1, when t is equal to 0. And y, when we go from t equals 0, y is -1. When t is equal to 1, y has gone up to 7. So y has increased by 8. So y increases by 8 when t increases by 1. So our delta y over delta t, our change in y is increased by 8 when t increases by 1. So our function for y of t will be -1 plus 8 times t. So y of 0 is -1 plus 8 times 0, or -1. And y of 1 is -1 plus 8 times 1, or 7. So that checks out. When t is 0, we get the point 2, -1. And when t is 1, we get the point -4, 7. If we check this out on a calculating machine, first let's look at, in function mode, if we look at the graph, y equals 7 minus 4/3 times x plus 4. Oh, we're not actually going to get the 2 points. I want -4, 7. So I need to go, let's expand my window. Let's zoom out. That was a little bit excessive. All right. So there's my line. If I trace this, when x is equal to 2, y is equal to -1. When x is equal to -4, y is equal to 7. So this is the line that we're looking at. Note that if I put in the other line, -1 minus 4/3, oops, I forgot to hit 1, -1 minus 4/3 times x minus 2, we see the lines are right on top of each other. So if I trace the red line, when x is equal to 2, y is equal to -1, and when x is equal to -4, y is equal to 7. So everything is working so far. Let's switch to parametric. And put in our parameters. So now I'm going to put x as 2 minus 6t and y as -1 plus 8t. And we see we get the same line. And we also see, even though it went pretty fast, we also see that it went from right to left. That was the direction that we got when t is equal to 0. We are at 2, -1, and when t is equal to 1, we're at -4, 7. If I trace and I put in a t of 0, I'm at the point 2, -1. And when I trace and put in the point t equals 1, I'll be at -4, 7. Any questions? It's not about one of these descriptions, y as a function of x or parameterized x and y. It's not about one of these being faster or being better or being more efficient. It's just different. Too often we look at multiple ways of doing something in math and we try to say one is better than the other because one method is faster than the other. But the only reason that method is faster is because we've had a lot of experience doing an old method, so we're fast at it. And the new method requires us to slow down and think about things, and that's why it's slower. Never mind the fact that speed is not the point, because if we want things to go quickly, there's an answer for that. Very few people are going to calculate faster than we can calculate on a machine. So if someone is like, oh, don't do it that way, this way is faster, they are arguing for you to not know something, which is exactly the opposite of what we're trying to do here in school. We want you to know things, not know things. Anybody who's afraid of you knowing something should not be trusted. You know what I mean? So it's important to realize that one of the things that makes this more difficult, besides the fact that it's new and we've been doing y equals mx plus b since elementary algebra, is that we get to choose the parameters. I happen to choose t equals 0 for 2, -1, and t equals 1 for -4, 7. It didn't have to be that way. If I want, and in particular, if I want my line to go from right to left, then I might want to switch those. Maybe I want t equals 0 to be at -4, 7, and t equals 1 to be at 2, 1. In which case, instead of x decreasing by 6, x will increase by 6 if we're trying to go the other direction. So let me change my description. Instead of 2 minus 6t, let's start off at -4, it's not -44, and increase by 6 whenever t increases by 1. And instead of y starting off at -1, let's have y start off at 7, and instead of increasing by 8, let's have y decrease by 8 every unit. Now if we graph the line, we see it go the other direction. Note that on my window, I've set this up to plug in values of t from -10 to 10, because I knew that that would cover everything on this screen. If I only graph the values of t from 0 to 1, I'm only going to get the line segment connecting those 2 points. Starts off at -4, 7, goes to 2, -1, and then stops. If I increase the t max to 10, then it still starts at 0 and goes in that direction. So if I wanted to cover everything, I just start t before it shows up on the screen to get everything, at least everything on the screen. If we zoom out far enough, we'll still just be looking at a line segment from t equals -10 to t equals +10. Any questions? How's everybody okay? So here we had this equation where, do I want to do this? I don't think I want to do that yet. I want to skip that example. So let's suppose that a particle moves along the curve where x of t is 2t plus e to the t, and y of t is 3t minus 4, and t is time. So what we've set up here is a position at time t. So we're looking at a position at time t. So this is where derivatives are going to make their appearance. We're looking at a position at time t. So you can probably guess that derivatives are going to show up, because if I take the derivative of the position at time t, or with respect to t, then we're going to get the velocity. Let's take a look at what this curve looks like. And we're going to use our calculator so we can see what direction things are going in. So get rid of my line. Let's graph 2t plus e to the t. 2t plus e to the t. And 3t minus 4. And if we trace when t is equal to -10, we're way at -20 to 34. What's happening at t equals 0? We're at the point 1, -4, and then at t is equal to 1, we move to 4.71 and -1, and when t is equal to 2. So we can see the path. And also, if I just trace different values of t, we can see where the particle is headed at these different values of t. And it was moving from left to right. So let's find the velocity of the particle at time t equals 0 and at time t is equal to 1. Let's find the velocity actually, let's find the equation of the line tangent to the curve at t is equal to 1. Let's find the equation of the line tangent to the curve at t is equal to 1. We want to find the equation of a tangent line. We need a point, and we need a slope or a direction. If it's a tangent line, that means the direction comes from derivatives. So taking a look at the parts, the things that we're looking for. We want the equation of a line. And that says we need a point and a slope. Since we're looking for a tangent line, we're going to get our slope from a derivative. So let's first get a point. The position of the particle is just given by the two functions x of t and y of t. Now we want to know what's going on when t is equal to 1. So let's find x of 1 and y of 1. So x of 1 is 2 times 1 plus e to the 1. So if we plug in t is equal to 1, we end up with 2 plus e to the 1, which is just going to be 2 plus e, write the exact form. Y of 1 will be 3 times 1 minus 4. So y of 1 is negative 1. So now we have a point, 2 plus e, comma, negative 1. That's the same point that we had when t is equal to 1. So if I trace it with 1, 2 plus e is 4.718281828 and so on, and negative 1. So things match so far. So far, so good. Now we need something about a direction. And for a tangent line, direction comes from the derivative. So we need derivatives of our functions. So I need x prime of t. Oops. I need x prime of t. X prime of t, the derivative is going to of 2t is just 2. And the derivative of e to the t is e to the t. I need x prime at 1. That's going to be 2 plus e to the 1 power. Which is just going to be 2 plus e. Now keep in mind, this is the derivative of x with respect to t. So this is how x is changing with respect to time, not with respect to y. Y prime of t, the derivative of 3t minus 4 is just 3. So y prime at 1 is just going to be 3, and then we're done. There's nowhere to plug in the 1, so we just get 3. Also, this is not the slope. This is going to be the change in y with respect to t. So now we have to decide, are we going to write the equation of the line with parameters, or are we going to write the equation of a line in point slope form? It makes sense to parameterize it because our curve is parameterized. So let's do that. So the line the horizontal part of the line, I'm going to pick my point to start, 2 plus e. That's where it starts. And it increases by 2 plus e. That's the change in x with respect to time whenever t is different than 1. In the y direction, y starts off at -1 and increases by 3 whenever t is different than 1. Oops, I just wrote all that off camera. This says x is equal to 2 plus e when t is equal to 1, combined with this minus 1 out here. And this plus 2 plus e says, and x increases by 2 plus e every 1 unit when t increases by 1. That's the read that we get from that equation. The y, it's a little bit simpler. This -1 says that y is equal to -1 when t is equal to 1, when t is equal to 1, and y increases by 3 when t increases by 1. Let's put this equation into our calculating machine and see what we get. So my x coordinate should look like 2 plus e. Plus 2 plus e times t minus 1. My y coordinate is -1 plus 3 times t minus 1. Let's see if this worked. If we trace, still drawing, trace when t is equal to 1, we see that that coincides with the graph. They're at the same point and they're going in the same direction. So the red line is tangent to the blue curve at t equals 1. Any questions?
Yes, please, Professor Leach. On this example, so we see, first we see the points here. So let's say the point x1, then we have equal 2 plus e, or y1, then we get -1. So that's the points.
Yes.
And then when we get the slope, we set x to prime derivative. Then we plug 1 in, we have the change in x.
Change in x with respect to t.
Okay. And then come to the y derivative, on the y derivative. And then we get, we plug 1 in, we get 3. Change y to respect of t. I get that point, but the last line, I have no clues where you get those, 2 plus e.
I need to write, so we're starting off at this point. X starts off at 2 plus e, and then x increases by 2 plus e whenever t increases by 1. So this is how x is changing with respect to t, because it's the derivative of x with respect to t. So we start off at 2 plus e and add 2 plus e a bunch of times. We start off at 2 plus e and add 2 plus e a bunch of times. It works just like the slope. If I write y equals b plus m times x, this b says y equals b when x equals 0. And the m tells us that y increases by m when x increases by 1. That's what b plus mx means. And this is just a variation. If I have y equals k plus m times x minus h, then y is equal to k when x is equal to h, and y increases by m when x increases by 1. And I'm just making a linear function for the x and for the y. So in the y column, in this second coordinate, y starts off, y is -1 when t is equal to 1. Y is -1 when t is equal to 1. And y increases by 3 whenever t increases by 1. That's what the slope means.
Oh, yeah. So the 3 is the slope, isn't it?
3 is the slope, the change in y with respect to t in this case.
Thanks. How about if we look on the left, 2 plus e, and then 2 plus e, t negative. Which one is the slope? Do we have the slope?
Which one is constant? Which one is the constant being multiplied by t?
Well, I will look at it again.
See that here's the change in y with respect to t. It's the +3 times the t, right? 3 gets multiplied by t.
Yes.
What's being multiplied by t in this expression?
Well, I will look at it again. Thanks, Professor.
It's the 2 plus e. 2 plus e is taking the place of the 3. The 2 plus e over here is performing the same role as the 3 is in the y coordinate.
Wow.
2 plus e is just 4.718. So we're just saying y is equal to 4.718. Y is equal to, or x is equal to 4, starts off at 4.718 and increases by 4.718 when t increases by 1. So this was a familiar problem. Find the equation of a line tangent to a curve at a given point. It's just in a new format where everything's parameterized rather than y being written as a function of x. All right, all the homework from chapter 4 is uploaded, and I can't remember when I set the due date. Due dates being only suggestions anyway. Oh, you have until October 31st for the last 2 homeworks from chapter 4. So keep working on those. This Sunday coming up is for the sections 4, 5, and 6 from chapter 4. Next week, we'll wrap up this parametric equations business and move on to our next big thing, which is going to be the definite integral. All right, so that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.
Thank you.